Global warming and lack of fossil fuels are the main drawbacks of petrol and diesel vehicles. And petrol diesel cost also increasing day by day. That's why people showing interest in electrical vehicles. These electrical vehicles working mainly depending on energy management system, nothing but battery. The main drawback of these electrical vehicles are long battery charging. That means we need to charge the electrical vehicle battery more time. And next drawback is limited driving range. The driving range also limited. We can't go for long distance on electrical vehicles. In order to eliminate these drawbacks, we will go for the hybrid electrical vehicles. Actually, the name hybrid itself indicates combination of different things. So here we are combining the different sources to our electrical vehicle. That's the main idea about these hybrid electrical vehicles. These are nothing but the electrical vehicles, but here we are taking the combination of different sources. That's it. That is the hybrid electrical vehicles. And here in our project, I am taking three different sources. That is nothing but first one is rooftop solar panel, nothing but PV panel, and then second one is fuel cell. Here I am taking the hydrogen fuel cell. Why hydrogen? Because it is easily available in water, biomass, etc. And hydrogen fuel cell is clean electricity, pure water and heat are the only emissions of fuel cells. That's why I am taking the hydrogen fuel cells here. And I am also taking one battery here. These are the three different sources I am taking for my hybrid electrical vehicle. And here I am taking the rooftop solar panel to charge this battery. So by using this, we can increase the efficiency and reduce the fuel cost. That's it. By using these three sources, we can eliminate the long battery charging drawback. Whenever solar is available, we can charge our battery while running electrical vehicle. And we can also go for long distance. And another advantage is whenever one or two sources are not available, that remaining source can power our electrical vehicle. That's the main thing. Whenever this solar and this fuel cell is not available, then battery can power our vehicle. Whenever battery and solar not available, this fuel cell can power our vehicle. That's it. That is the main advantage of this hybrid electrical vehicle system. But the thing is, in fuel cell output, we are getting the DC, right? And battery also need DC. And the solar panel output also we are getting the DC. Here we are getting the DC at the three outputs. And we can generally see batteries have the low voltage capability. It does not have the high voltage. If the battery have a high voltage capability, it has the more size, right? And in solar panels also we are getting the low voltages. So in order to increase this low voltage DC into required vehicle voltage, we need to step up this voltage, right? We need to boost up this voltage. That's why we are connecting the DC-DC converter here. Okay. And why I am go for multi-input? Because here for this DC to DC converter, what we are taking? We are taking the three inputs like solar and fuel cell and battery. Like this we are taking the three inputs, right? Means that is the multi-input. So that's why this circuit is called as multi-input DC-DC converter. DC to DC converter means we are boost up this one voltage to another voltage. That's why I am taking the multi-input DC-DC converter for our electrical vehicle. And you can observe the PV panel arrow symbol is only like this direction, right? So this is like this direction only. And fuel cell also direction is like this only. But battery have both directions. Why both directions? It has the bidirectional capability. Means it can charge and it can discharge. Means we need to take the power from the battery and we also give back power to the battery to charge the battery. Okay. That's why here we are getting the bidirectional symbol. That's it. So finally we need to design one multi-input DC-DC converter for our three sources. That's the main theme and that's our title. A novel means new. A new step-up multi-input DC-DC converter. That is what we call here multi-input DC-DC converter. For what? For hybrid electrical vehicle application. That's our title. I think now you can get the clarity about this title, right? We need to design a new step-up multi-input DC-DC converter. For what? For our hybrid electrical vehicle. That's it. That's our title. And here is our circuit. This is our proposed circuit diagram. Nothing but 3 input DC-DC boost converter. That's what we required, right? So here we are taking the 3 input sources. Here I am taking as VPV, nothing but the solar here. And here I am taking this DC source as fuel cell, VFC. This is nothing but fuel cell. And here I am taking battery. Okay. These 3 are inputs of our DC to DC boost converter. And this whole converter is formed of 2 conventional boost converters. So like this, I formed a 2 boost converters. Okay. And this converter circuit is suitable for hybrid systems. It is also suitable for power management between these 3 sources and control part. And coming to the elements, this inductor L1 and this inductor L2 are input filters of this solar panel and this fuel cells. Okay, these 2 are the input filters of this solar cell and this fuel cell. And this L1 and L2 is connected in series with these solar and fuel cell sources, right? Why? Because it can act as a current sources. That's why I'm taking inductor L1, inductor L2 are series to our sources. It can act as a current sources. Okay. And this resistance R1 and resistance R2 are equivalent resistance of this VPV and this VFC, fuel cell and solar cells. Okay. And this RL is the load resistance, we already know. And it is connected to the DC bus because we are getting the output as DC, right? And this S1, S2, S3, S4 are power switches. And this D1, D2, D3, D4, D5 are diodes. And this capacitor C1 is used to increase the output gain. And this output capacitor C0, nothing but the V0, will be act as a output filter. And this whole circuit operating in a continuous conduction mode to produce smooth current with the least possible amount of current ripple. That's it. These are the things we need to know about the circuit elements. And the working operation for this converter will be divided into 3 states. In first state, only PV and fuel cell is used. Here battery is not used, totally not connected. And in second state, PV and fuel cell as well as battery also connected, but here battery in discharging mode. And coming to third state, here also the load is supplied by PV and fuel cell and also battery, but here battery is charging mode. That's the 3 states we are having for our proposed circuit. Okay. In that each state has 3 or 4 different modes. For example, here I am taking the first state. Here we have the 3 different modes. This is the mode 1, this is mode 2 and this is mode 3. Like this I am having. So here in first state, what we are discussing, here battery is completely not connected, right? That's why here battery path is not connected. That's the first state. And here we have the 2 common paths, nothing but the 2 current flowing paths, that is through D1 and S4, or it can be flow through D3 and S3. These are the common paths for current flow. But here in our project I am taking only S3 and D3. That's why current is flowing always in this direction, like in mode 1 and mode 3 and mode 2. Okay, that's why it is only showing S3 and D3 always. And this D1 and S4 path is I am taking as alternate path. Okay. And this first state, switch S3 is completely turned on. That's why this S3 is always in on condition. And switch S4 is completely off. That's why this switch S4 is completely off condition. Because I am taking this is the alternate path, right? That's why it is the completely off state. Okay. In first mode, this is the first mode. Here I am turned on S1, S2 and S3. That's why switch S1, S2, S3 is on. And in second state, I am turn off S1 and I turn on S2 and S3 again. And coming to the third mode, again I am turn on S2 and S3. That's it. These are the 3 different modes in state 1. If you observe the graph, then you can easily get some idea about these operation conditions. Here I am taking the first state graph, nothing but waveforms. Here I am taking, this is S1 switches, S2, S3 and S4. And here I already told you in first state, switch S4 is completely off, right? So here S4 is completely off. That's why it does not have any turn on pulses. That's why this S4 is completely turn off. Nothing but total 0. And here I already told you switch S3 is completely on. That's why this switch S3 have total on condition. And here I am turn on S1 and S2 is alternately on and off like that. That's why it is sometime on and sometime off like this. Okay. And this inductor L1 and this inductor L2 are continuously charging and discharging, right? By turn on, switch off and on. Like that here, inductor L1 charge, discharge, charge and again discharge like that. Here also inductor L2 also charge, discharge like that. This is the waveform we need to observe. Okay. Like this we have second and third states also. So we can see that remaining states also. This is second state and this is third state waveforms. Okay. But in first state we only connect fuel cell and PV, right? Not battery. That's why here we have only 3 states. But here in second state and third state we are connecting the battery also. But in one state it is charging and another state it is discharging. That's the another thing. But here we have connecting battery, right? That's why it has the 4 modes, 1 2 3 4. That's why it has the 4 mode of operations in second state and third state. Okay. And coming to here, in second state switch S4 is completely on. That's why it is totally on pulses, and we can turn on S1, S2, S3 as on and off like that. Here also inductors are charging, discharging like that. Okay. And coming to third state, here switch S3 is completely off. So here S3 is completely off, and this S1, S2, S4 are we are turn on, turn off. Okay. Based on that, inductors are charging, discharging like this. Okay. These are the waveform for these 3 different modes. Like this we can operate our circuit. And this is the graphical representation of voltage gain, and this top one is the our proposed converter voltage gain, and this bottom one is the old, nothing but the conventional converter. Okay. But if you compare these two, our proposed converter have the high voltage gain. That's why we are getting the more voltage gain. More voltage gain means more efficiency, less losses. That's the thing we need to know. And next thing we need to know is power management strategy for our hybrid electrical vehicle. This is the flowchart for that one. And here this is the P command, nothing but the power which is required for our electrical vehicle. Okay. And here PPV means solar power. And here PFC means fuel cell power. And here PB means battery power. That's it. Here no need to confuse about this flowchart. Just do simple things. Here we have 3 sources, right? Nothing but solar and fuel cells and battery, and we need to give these 3 powers to our electrical vehicle. Okay. So first of all we will note the required power value. So that is nothing but the P command, what we need. Okay. First of all we need to check whether the power which is coming from the solar is equal or more than for our electrical vehicle. If it is more than our electrical vehicle, then we will see the battery capability. Okay, is it battery capability is minimum or maximum? If this battery capability is minimum, then we need to charge this battery, right? So that's why it will be charged. Okay, if this battery is already charged, then we don't need to charge. That's the thing we need to know. If this solar power is not equal to this P command, means we are not getting the required power from the solar cell, then we will go for the fuel cell. Okay, first of all we need to check this solar power, how much we are getting. That less than power will be taken from this fuel cell or battery. Okay, that's it. That is the thing we need to know for this flowchart. Okay, now you can observe, it will be easy for you. Here I will show you some waveforms also. After completion of the simulation, you are getting the results like this. Okay, and these are the waveforms for only first state. So here this is the VC1 and this is the V out, means we are increasing that voltage, right? That's why our circuit is known as the multi-input DC-DC boost converter, nothing but the step-up converter. That's why here we are getting the more voltage at the output. And here our inductor L1 and L2s are gradually charge and discharge based on diodes and IGBTs. Okay, so here in first state switch S4 is completely off, right? That's why the current across this switch S4 is completely 0. And switch S3 is completely on, right? That's why it is the completely on condition. Okay, this one. And that remaining 2 switches S1 and S2 is simultaneously on and off like this. Okay, and these are the current of the diodes and these are the voltage of the diodes, and this is the voltage of the switches IGBTs. Okay, these are the graphs we are getting for the first state. Like this we are getting the second state and third state also. Okay, now we will see the MATLAB simulation file of this circuit. This is the MATLAB file for our project. Okay, and this circuit is for only first state. For that remaining 2 states we also have 2 circuits. Don't panic about this circuit. Whatever we have in this figure, that only I connected in MATLAB. Here we have one DC source as solar PV and resistance and inductance. Like that only I am connecting here. So here I am taking the VPV and the inductor and resistance, right? Like this I am taking solar panel and inductor and resistance. Okay, and here I am taking the one current measurement in series, like whatever we have in ammeter in laboratory. In ammeter we connect series, right? That's why I'm connecting the current measurement in series with the inductor to measure the inductor currents. And next thing what we have the fuel cell and battery also, right? Here I'm taking the battery and here I'm taking the fuel cell as DC source. And what remaining, we have a 4 switches and 5 diodes and 2 capacitors, right? So here I'm taking the 4 switches, switch S1 and S2, S3, and this is switch S4. Okay, and we have 5 diodes, right? So in that, this is diode D1, this is diode D2, this is diode D3, this is diode D4, and this is diode D5. That's it. These are the diodes and switches. And coming to capacitors, here we have the capacitor C1 to increase the gain, and this is the output capacitor filter C2. Okay, whatever we are taking ammeters, nothing but the current measurements, we also take the voltage measurements also to measure the voltage, right? So here I'm taking the VC1, nothing but the voltage measurement across this C1. How we are connecting the voltmeter in our laboratory? We are connecting in parallel, right? That's why I'm connecting the voltage measurement in parallel to our capacitor. You can connect the voltmeter in parallel, ammeter in series. That's it. Okay, like that you can take for every diode and every switch voltage measurements and current measurement to measure the currents and voltage across that switch. Okay, and here I'm taking the power GI in discrete solver. Without this one we can't run the circuit. And coming to here, we are taking the switches, right? 4 switches that are the bidirectional switches, nothing but here I'm taking the IGBTs. Okay, in IGBTs we need to give the pulses, right? Switching pulses. So where I'm taking the switching pulses, I'm taking the switching pulses from here. These are the control block, nothing but the control system blocks. In control systems, we need to take the one reference value and one actual value, right? Here I'm taking the one reference value and here I'm taking the one actual value and give it to one sum and give it to PI controller. In this subsystem, we're having the PI controller. This is proportional gain and this is the integral gain, right? And the output of the PI controller will be given to the pulse width modulation. Here I'm taking the carrier wave here, and here I'm taking the reference wave. So I'm giving to the one gradient resistant conditions and give it to the switch S1 through the OR gate. Okay, so like this we need to control the voltage also, right? So for top one we're controlling the current and here I'm controlling the voltage. Here this is the reference voltage what we are want and this is the actual voltage what we are getting. And again we are taking the one PA controller and give it to the same pulse width modulation and give it to the switch S2. Okay, like this we are turn on S1 and S2. We already know in first state we need to completely turn off this switch S4, right? That's why I'm taking the 0S S4 and in first state we need to turn on the S3 all time. That's why I'm taking the 1 as the S3 because we need to turn on the switch all time and S4 will be turned off at all time. That's why I'm taking like this switches. Okay, and these are the PA control and pulse width modulation. I also explain it clearly about this control system and pulse width modulation in previous videos. You can watch that videos about this complete information like why PA control, why pulse width modulation, how they are working. Okay, and these are the scopes I am connecting to see the waveforms of our inductor and capacitor values and switches currents and voltage like that. Okay, so whatever we are measuring in voltmeters and ammeters, nothing but the voltage measurements and current measurements, we can able to see here that waveforms. Okay, so now run your circuit. After running, just open your scopes one by one. Here I am opening the V0 and VC1. These are the two voltages across the capacitor. Here I am getting the 110 volts at the output and here we are getting the capacitor across C1 is 55 volts. Means we are step up the voltage, right? We are boosting the voltage. And here I am taking the IL1 and IL2 for first state. These are the inductor 1 and inductor 2 currents. You can zoom it to see the exact waveform. So here the inductor L1 and L2 are gradually increasing and decreasing, right? So these are the L1 and L2 values. And coming to the switches, these are the 4 switches currents. In here we are turn off the switch S4 completely, that's why it is like 0, near to 0. Okay, and we are turn on the S3 completely, so that's why it is waveform like this. And we turn on and we turn off the S1 S2 alternately, that's why it is like this. Whenever it is on it will be high, whenever it is off it will be 0. So like that we can also able to see the voltage of the switches. These are the voltage of that switches. You can zoom it if you want. Okay, like this. And coming to diode currents, it will be like this. These are the diode currents and these are the diode voltages. This is the waveforms we are getting for our first state. Like this we have the second and third state also. Just we need to change the switching pulses according to that state. That's the thing we need to change. That remaining all circuit elements and connections and scope parameters all are same. Just we need to change the switching pulses according to that state. Okay, that's it. This is the simple project and this is the very important thought for future electrical vehicles. Here we are eliminating the long driving range and we also decrease the charging, long time charging. Whenever the solar is available, we can easily charging our vehicle. These are the main things we need to require for our circuit and our concept. Okay, if you want this project, contact me. I will give you and I also provide the IEEE base paper in the video description. You can go through it.